So now we are going to see another example of CFX expression language. We have to set inlet temperature to 300 Kelvin for the first 19 iterations and then raise it to 350 Kelvin after 20 iterations. What we do is we write an expression called as inlet temperature, which is 300 Kelvin plus 50 accumulated time step minus 20. So what will happen is this will be initially 300 for the first 19 and then it will be 350 after 20 iterations. So when we plot it here, we can view the expression, and then we have to go to the boundary condition, and instead of static temperature we input the expression. So what will happen is for the first 20 iterations the temperature would be 300, then it will take boundary condition as 350 Kelvin. Using the CFX expression language, we can also define customized one-dimensional linear or three-dimensional cloud interpolation functions. So we go to user functions, insert user function, and the insert function is defined as pressure versus time. So here we have to say that interpolation method should be used, and we define pressure versus time as the data. By right clicking, we can import this from an Excel file or any other file that we want, and after that this can be used as a boundary condition in the simulation. That is, pressure will be changing, the boundary condition pressure will be changing as a function of time step or a time instant. So this is what the ramping function will look like. If you want to input the expression or function, user function as a relation or as a function of accumulated iteration number. So we can define user function as a function of a time step. You can define user function as a function of iteration number. You can directly use this time step itself. What we can do is, this is the time step. We will say that this is a time step. Change the time step as the iteration changes. So we can define anything using the user function option as a function of other variables or other iterations or iteration number. Again, we have used the interpolated data here to define the user function. Number of iterations is dimensionless and time step is in seconds. So in this example, we are changing the time step as a function of iterations. So a list of iteration is shown here, and list of expression is shown here. We have created a ramp expression, that is the expression to ramp up the time step. And then in the solver section, or when we are actually calculating the solution, instead of physical time step giving a single time step value, we are going to give this function, the ramp, as a time step input. It is also possible for advanced users to access integration functions within the solver. These quantities can be entered into the expression and be monitored. We will discuss the details in the output control lecture. Also, calculation of non-local integrated quantities at name location can be done. So what we can do is calculate the area average of CP on an isosurface. For that, the expression is area average, which is a ready-made function of CP at the isosurface. Mass flow of a particular fluid along through a locator can also be done, which is mass flow of a fluid at slice 1, that is the locator. So at a locator syntax must always supply a location. So after you have at, there should be a location. Let us see a list of monitor expressions. Below is the list is a partial list of some functions which are available to monitor expressions within CFD post. So we have area bracket at location. The operation is area of a boundary or interface. It is valid for any 2D region or interface, that is boundary or interface. Area x at location function, it is area weighted average. Area underscore x at location function is area weighted average of a variable on a boundary. Any 2D location can be taken as a valid location. Similarly, we have area weighted y, area weighted z. Area underscore x at a location gives the area projected in the x direction. Similarly, area underscore y gives in y direction, area underscore z gives in z direction. Area average variable at location gives the area weighted average of a variable on a boundary. Any 2D region can be selected as a location. Area integral variable at location gives area weighted integral of a variable on a boundary. Any 2D or location can be taken as any 2D region can be taken as a locator. Average at location gives arithmetic average of a variable within a domain or subdomain. Any 3D region is required for this as a location. Fluid dot force at location gives the magnitude of a force vector on a boundary. Any 2D region can be taken as a valid location. We also have fluid dot force x at location, which is the component of the force vector in the x, y or z direction. Any 2D location can be taken as a valid location. Inside at location The operation is similar to the subdomain variable, but it allows a specific 2D or 3D location to be given. Any 2D or 3D named subdomain of the physical location on which the expression is evaluated can be taken as a location. Mass at location, the total mass within a domain or subdomain is the output from this function. Any 3D region can be taken as a locator. Mass average gives the mass weighted average. Any 3D region is required for this, and mass integral gives the mass weighted integration. Any 3D region is again required as a locator. Fluid dot mass flow at location gives the mass flow through a boundary. Any fluid surface can be taken as a location. Examples are inlet, outlet, openings, fluid interfaces. And fluid dot mass flow average at location gives mass flow weighted average on a boundary. Again, location can be inlets, outlets, openings, and fluid interfaces. We'll continue the list of monitor expressions. Fluid dot mass flow average absolute gives the absolute value of flow weighted average of a variable on a boundary. Any fluid surface like outlets, inlets, openings can be taken as a location. Mass flow integral at location gives the mass flow weighted integration on a boundary. Again, we require flow boundaries for that as a location. Maximum value of a variable at location gives the maximum value of a variable within a domain or subdomain. We require a 3D region as a location. Min val at location gives the minimum value within a domain or subdomain. Again, 3D region is required as a locator. Probe variable at location returns the value of a specified location variable on a specified probe locator. Any point object is needed or location is needed as a locator, that is Cartesian coordinates or any point entity or object. RMS average at location gives the RMS average of a variable, and sum at location gives the sum over all over the domain for which the 3D region that we specify as a domain. So to summarize this particular lecture, the CFX expression language allows the user to create expressions that can be used in CFX pre, CFX solver, and CFX post. Next, we will see the CFX command language and how to modify the solver output file. Thank you for attending this particular session. See you in the next lecture in this course on CFD modeling using ANSYS CFX.